Every once in a while, you find somebody's chart and it's like, wow, I think I got that.
Well, no, it's a little bit earlier, but I think most of you are already here. So please take seats. I think you'll be seated by your ID order. And we'd like to begin the first session. The first lecture is a Sixth Hope meeting. It's delivered by Professor Brian Schmidt. As you may know, this Hope meeting had 7 Japanese researchers taking the role of moderators. For the participants, a moderator is assigned to each lecture in order to moderate the lectures as well as the group discussion sessions. We would like to introduce Professor Makoto Natsume, Professor of KEK, who will act as the moderator of this session. Professor Natsume, please.
Thank you. Morning, everyone. I'm the moderator of this session, Makoto Natsume from KEK, High Energy Accelerator Research Organization. I'm a particle physicist, theoretical particle physicist. It is my pleasure to introduce our first lecturer, Professor Brian Schmidt, a Laureate Fellow and Distinguished Professor at the Australian National University's Mount Stromlo Observatory. He was born in 1967 and grew up in Montana and Alaska. Excuse me. He graduated from University of Arizona in 1989. He then went to Harvard and received his PhD in 1993. After the graduation, he formed the so-called High-Z supernova search team. You probably know our universe begins with a Big Bang, and the universe is expanding. In 1998, his team and another team, the Supernova Cosmology Project, both found the expansion is accelerating. This discovery was chosen as the breakthrough of the year by Science magazine. Since then, he received many prizes and honors, including the Shaw Prize for Astronomy. But I cannot list them all. There are many. In addition, he has another talent. He is a professional winemaker. He owns a vineyard and winery. But I must quickly add that he didn't bring his wine with him here So please do not ask one. Now, in 2011, he received the Nobel Prize for Physics, quote, for the discovery of the accelerating expansion of the universe through observations of distant supernovae, unquote. You will hear more details from him. Today, he will tell us about cosmology as an example of the process of discovery. Professor Schmidt, please.
Thank you. Thank you for everyone. It's a great honor to be the first cab off the rank, as we would say, at my part of the world. So I'm going to talk to you about cosmology, and I'm going to use it and tell the story of cosmology and what we know and my own research. But I'm going to point along the way to some seminal ways in which cosmology has helped form how we undertake science and how we think about science. And one of the beautiful things about astronomy is that it is so esoteric. It brings things to the forefront, where you really just have to come to terms with how science works in its purest form. We don't let data somehow get in the way sometimes. So I'm going to start, and when we think about astronomy, really is probably the oldest of the sciences. I often say it's the second oldest profession. And we're going to go right back to Ptolemy, the Greek/Roman philosopher/scientist, who first started thinking about, in detail, how the planets and stars worked. And he came up with the Ptolemaic system, which was used, although he did it just around 2,000 years ago. His method of understanding the cosmos was still in place in 1500 AD. We really made no further progress after him, which is one of the reasons why we call it the Dark Ages, those periods of time, because we didn't do scientific research for many hundreds of years, at least in the Western world. And so we were stuck with the Ptolemaic system, which described how planets went around the Earth in quite elaborate detail. And the reason why, for example, Mercury did this spirographic pattern is because the Greeks had some axioms. Axioms are things that you hold to be true, but you do not try to be true. You do not actually test to be true, which is that the Earth is at the center, and the objects travel in circles. And so they had to make their system fit that. Why did they choose those axioms? Well, it must be so. Now, mathematics is built on axioms. A equals B equals C, therefore A equals C is an axiom. Now, we take that to be true because it's part of the logic of mathematics. But in this case, it's not something we had to take to be true. And to make it so, they had to do all sorts of interesting things called epicycles, where you would take a circle and you would have the object as it went around the Earth, for example, Venus, go in a circle, and that circle would be offset from the Earth. And then within that circle, it would be going through another tinier circle. And through that system, Ptolemy was able to predict very accurately where the planets went across the sky compared to anyone else. And that's why his system was used. They needed to predict things like Easter in advance. How'd they do it? They used the Ptolemaic system. So along came Copernicus 1,500 years later, and he transformed that idea of the axioms, where the Earth is at the center and things travel in circles, and he got rid of one of them. He still had things traveling in circles, but he had an additional piece where the sun was at the center. And then instead of those very elaborate patterns, he could simplify it to a bunch of circles around the sun, of which the Earth was just one of those. A radical idea that he wrote up and did not get much traction when it was first written up, because his system did not predict where the planets were in the sky better than what the Ptolemaic system did. Indeed, it did it worse, because he only had circles to work with. And it turns out, of course, things travel in ellipses. And he hadn't worked that out yet. But this was a much simpler idea. But was it reality? Well, the reason it became reality is because Galileo went out and invented technology in the form of a telescope that could look at the stars. And when he looked at, for example, Jupiter, so what it would have looked like to him, he saw 4 moons that orbited Jupiter. Clearly, the Earth was not the center of that system. And then he looked at Venus, and he saw that when Venus was a long ways away, on the other side of the sun, as it turned out, it was full, like the moon. And when it was nearby, it was big and a crescent shape. That only made sense if Venus went around the sun, not around the Earth. And so Galileo is the person who made Copernicus's idea a reality. You have an idea, you have an observation, and by working together and testing things, you get a theory that you believe and then you can expand on. Galileo was one of the first people to sort of believed in testing axioms. He believed in asking the question, is the Earth at the center? Do objects travel in circles? Do 2 objects of different masses fall at different rates, as the Greeks said, and he was taught in the late 1500s? Or do they fall at the same rate? In the 1580s, people were still being taught that a heavy ball falls faster than a light ball, even though you could go and test it yourself and see it wasn't true. So the next step came along with Newton. And Newton, we think of being the father of modern science. And he was the first person to really put together a mathematical framework. And he could then use that mathematical framework to go through and figure out, for example, that if objects are attracted by gravity by the square of the distance, then they would travel in the ellipses that Kepler had observed the planets actually traveling on. And through this, his book, The Principia, he sort of laid out a mathematical framework, which we still use today. And that framework allows us to precisely predict things, and with precise predictions comes the ability to falsify. And that is incredibly important. It doesn't matter if you're a chemist, a biologist, or a physicist. Is falsifying things you think to be true is the core of our business. That's how we learn. But predicting things is also the core of business. That's what makes us useful. When we can take the science that we do and predict things, that's why people invest billions upon billions of dollars in science. Because it's useful. All right. So let's see how this played out within my field. The next big advance were being able to build big telescopes. Herschel built this huge 30-footer, not 30-foot wide, 30-foot long. I think it was about 30 inches across. And he was able, as scanning the skies, to find the first planet that had ever really been discovered. All the other planets had been seen by our eyes, by our forefathers. And he saw this as this greenish ball that moved slowly across the sky. It didn't look like a star, and it had a motion that meant it was a long ways away, and it had to be actually quite big. So technology, rather than an idea, brought about the discovery of Uranus. But when they went through and they saw how Uranus was marching through the sky, it was soon realized that it was not traveling the way Newton's laws said it should be. So that brought an idea, a question. Were Newton's laws wrong? Or maybe an easier idea that was brought up by a mathematician, Laureate, in Paris, that all you needed to fix that motion that Uranus was going across the sky was another planet. A planet that he could predict where it would be, and in a sign of times to come now, the Germans and the French actually worked together in a period where they're mainly at war, and Leverrier sent off his predictions, and the German Galilei in Berlin promptly looked where this new planet should be and discovered Neptune. Now, again, we had the idea. I think there might be a planet there, but it becomes a reality when you test that prediction and you see what you expect. We look at gravity. Newton's laws had remained essentially perfect in any way they had been tested up through the early 1900s. And then one day, Einstein in 1907 had an idea. It's a very subtle idea. The idea was that you could not tell the difference between gravitational mass and inertial mass. That means that the acceleration due to moving quicker and the acceleration due to gravity, in his mind, had to be equivalent. I mean, there was no way, if, for example, you were in a box, you could not tell if you were in a rocket ship accelerating at 9.8 meters per second squared, or if you were stuck in the lift here at the hotel, just sitting there being accelerated by 9.8 meters seconds per squared. If you're in a box with no other information, there's no way to tell the difference between those two accelerations. That was the simple idea that Einstein had. Now, it was a hard idea in practice to figure out, because it took Einstein 8.5 years to go through and figure out what that simple idea meant for physics. And it turned out it allowed him to drive his field equations, and it predicted that space would be curved. These were big ideas, but it was an idea, and it fractured the world at the time. People who thought it was just crazy, and then a few people who thought it was brilliant, it had to be right, who went out and therefore tested his theory. And so Alfred Eddington, very famous Cambridge astronomer of the day, went out and organized for 2 eclipse expeditions. And the idea, and here are the actual images from those expeditions, more about those later, you could go through and you could see the stars during the during the eclipse, and then you could wait until the sun was out of there, and so the sun was no longer bending space, which would cause the positions of those stars to change when the sun was in that part of space. So when you went and waited for the sun to be gone, a few months later, you could look back and you could see, had the stars moved as Einstein's theory of curved space predicted. And in 1919, Eddington announced to the world that Einstein's theory was vindicated with great aplomb, and this is the New York Times article from the time, "Lights all askew in the heavens. Einstein theory trumps. Stars not where they seemed or were calculated to be, but nobody need worry." Of course, we use that to figure out how I got here with the GPS, and I use that theory, so it is useful. Just wasn't obvious back then. All right, so what is reality? We take reality for granted. Most of you work in labs, you take it for granted. I don't get that luxury sometimes because things become ambiguous. We'll talk about this later on. I think we all know I'm holding something in my hand that's real, but ultimately, to my mind, the way I deal with reality is I say reality is a set of ideas which predict the observations we make. And it doesn't really matter, I don't make it any more complicated than that. What's gravity? In this room, I have to admit, I don't think of it within terms of general relativistic framework. I think of it in terms of Newton. I take that, I drop it, it's going to be accelerated 9.8 meters per second squared by the inverse square law of gravity. I don't think of it as being some relativistic framework because it's too hard. But when I get near a black hole, and I have to think about it, then I have to think of it in a relativistic framework because I know Newton's laws don't work, and they don't predict the things. So you can have an idea, but it's showing that that idea is right, and it's that mixture of the ideas and the observations, that predictions that work, that make us believe what is real and what is not. So let's go to cosmology. And now cosmology, to my mind, in the purest form, got started in 1917. Two big things happened in 1917. One of which was this person, Vesto Melvin Slipher, went through and he took the light of galaxies, spread them out into spectra, looked at the atomic transitions, and he noticed that the light coming from these nebulae, as they were known, we didn't know what these things were, these nebulae looked like the light of stars, but they were shifted redward. All the wavelengths were moved redward compared to what the sun's spectrum would look like. So he could immediately tell these things looked like they were made up of the same stuff stars are made out of, but their spectral shift indicated through the Doppler shift that these things were somehow moving away from us. Now that was a conundrum in 1917, when you go through and you measure the velocity, all these nebulae, and they're all moving away from us. There's a couple that weren't, but of the 50 objects he looked at, I think 48 were moving away from us. That sort of goes against the Copernican principle, if you think about it. The Copernican principle says we're not in a special place in the universe. All observers should see what we see. Now that's an axiom and something we can test. But it's a pretty strong axiom and you don't necessarily want to break. And so suddenly we have most of these things moving away from us, seeming to indicate that we're a special place in the universe. Not a very popular one by most accounts, it would seem, but a special place. Now, how was this resolved? Well, in 1917, Albert Einstein, for the first time, used his general relativistic field equations. And to remind you, this is the tensor form of those field equations. Those are 16, that's a short form way of writing down 16 nonlinear equations. They're all coupled together. Try to solve 16 nonlinear partial differential equations simultaneously, and you'll realize you don't get very far. That's why there's only a few solutions to general relativity. We'll talk about them later on. But he was able to do something that Newton was never able to do, which is he could say, imagine I have a universe that's full of stuff and goes on forever. What happens if I apply my equations of relativity to that universe? It turns out Newton did that, and he realized the only answer he could get that made sense was that the universe had nothing in it. There was no solution with Newton's laws that allows for a universe without end. The only solution is that there is no mass in it. So what he found in 1917 is that he solved for cosmology, but he got a surprise. His solutions for the universe were dynamic. Now, he didn't really know what that meant in 1917. We now know that it means that the universe is expanding. But at the time, it meant that the universe would be somehow in motion. But we didn't have, he looked around and said, the universe is not in motion like my equations are saying. So he invented a fudge factor. That's what theorists always do as the first step when they make a prediction that is not borne out in subsequent observations. They make a fudge factor because every theorist believes their theory is sacred. And that's the way theorists are built, and you wouldn't want them any other way. So Einstein did that. He added a constant to his equations. It's this constant. When he was born, that didn't exist. He added it in 1917, and it turns out, he didn't think of it in these terms at the time, that a constant is effectively saying space itself has energy. And if space itself has energy, it turns out it essentially makes gravity push rather than pull. And so by adding the right amount of this stuff to the universe, he could offset the pull of gravity by the push of this cosmological constant. And he thought make the universe static and well-behaved. Desperate measure, but it was desperate times. Now it turns out mathematically, if a butterfly flapped its wings somewhere in the universe was going to go into motion. It wasn't a stable solution. So it didn't work anyway. But it stayed with the field for 10 years, this little tweak. So let's go to 1920, and there was a very famous debate known as the Curtis-Shapley debate. It took place in the U.S. National Academy of Sciences in 1920 between two people who were arguing about what these nebulae were. And there was the idea by Shapley, who said, we are in an island universe. The Milky Way is the universe. That is what the universe is. There is nothing else. And he argued that our galaxy is huge. How could it be, the universe be any bigger than our galaxy? It is hundreds of thousands of light years across. And to remind you, a light year is how far light travels in 365.2524 days. So that's 300,000 kilometers per second times 86,400 seconds in a day times those 365.25 days. So that's many, many trillions of kilometers per year. These nebulae, well, they're obviously being repulsed and avoid the Milky Way center. If you look through the Milky Way, there's this big dark region where there aren't any of these nebulae, and the fact that these things are being shot out from the middle of the galaxy, okay, that's fine. Don't understand it, but we can explain it. Then there are these novae. These are new stars that appear in the Milky Way, and we can see them in the largest of the nebulae, Andromeda, and they're about the same brightness, at least the one that they had discovered, as in the Milky Way. So clearly these things are the same brightness. They must be the same distance. The Andromeda galaxy, the Andromeda Nebula as it was known, is the same distance as parts of the Milky Way. Furthermore, a person by the name of von Manen has gone through and taken pictures of the Andromeda Nebula, seen that it's rotating on the sky, and if it were a long ways away, as other people think, who think that's another copy of the Milky Way, it would be rotating at faster than the speed of light. That doesn't make any sense. And furthermore, Shapley said, I have measured the color of these nebulae, and their colors are completely different than the colors of stars and the color of the Milky Way. So you should not believe that these nebulae have anything to do with what the Milky Way is. Arguing against him, Curtis, who said, these nebulae are like the Milky Way. We are all galaxies made up of stars. He said, our galaxy isn't so big. It's 10 times smaller than what Shapley said. Other galaxies seem to have lanes of dust across them like our Milky Way. Maybe it is that our Milky Way is full of dust and we simply can't see the nebulae in the center. I have no idea, he would say, why these objects seem to be moving away from us. That didn't make any sense. Evidence that there were many much fainter nebulae within the Andromeda galaxy. These were unconfirmed reports that there were these little stars that were 1 million times fainter than the one object that was seen in 1885. And furthermore, he reported that Slipher's spectra of these nebulae showed that they had spectra that looked like stars. So I don't know about the colors, but he said they certainly their spectra looked like stars. And, oops. So what was going on? It turned out, that Shapley was considered to more or less have won the debate on the night, despite essentially all of his arguments for being wrong. And understanding why his arguments are wrong is important to think about how science works. He said the galaxy is huge. It turns out that was the one thing he was right on. He had figured out the size of the galaxy more or less correctly. But saying something is so big, how could it be any bigger? That just means you have a limited imagination. The universe is a lot bigger than even he thought. The nebula being repulsed and avoiding the Milky Way center, well, Curtis had that right. The Milky Way is full of dust. You simply can't see the things. The novae in the largest nebula of Andromeda, turns out that was a supernova, a different type of event than the novae that had been seen. There was missing information. They saw something that they had not realized what it was. The rotation measurement of Andromeda was just wrong. It was bad data. The measurement was flawed. You cannot see the rotation of the Andromeda galaxy. And Shapley's measurement of the colors of the nebulae was also wrong. Bad data. So there was some missing information. These novae were actually supernovae occasionally. And the idea that the universe was expanding was a missing idea. So how did we discover that the universe was expanding? And how did we solve that whole question of the island universes? It came from doing distances. Now, measuring distances in astronomy is not straightforward because we cannot lay down rulers between here and the nearest galaxy or star. Instead, we have to rely on how things appear. This is a fundamental difference between astronomy and most of the rest of science that we do. We don't get to invent experiments. We are sort of pack rats, and we troll through the universe of shiny things, and we bring together those shiny things and create our own experiments based on what nature provides. So it has an extra level of difficulty, and it's for this reason sometimes my physics colleagues think we're not real physicists, although they seem to have eased up on that view over the last 20 years. But it does make our discipline very challenging. So one of the things you can do is you can look at how bright an object is. Now, Newton realized that if you took a light bulb, or in his case, a candle, and you saw how bright it was and you moved it to half the distance, because the light is spread out over a surface area of a sphere, the object becomes fainter by the square of the distance. So we can look at an object, and if we see something to be 4 times fainter, we know it's 2 times further away. And that's what Hubble did. He went out and used new technology and ideas to literally measure the distance to the nearest nebulae. And using the ideas, and they came from none other than Harlow Shapley's group at Harvard. Here we have Henrietta Swan Leavitt and a team of women who were referred to as computers at the time. Interesting way the term has changed. They realized that there were types of stars known as Cepheids that have a regular pulsing frequency whose brightness is always the same. Their brightness and that pulsing frequency are related. Hubble then went out and used the new piece of equipment, the 100-inch Hooker telescope at Mount Wilson, a huge leap forward in technology and ability to look to the stars. And he looked at the nearest galaxy. Here we are on the 6th of October, 1923, with a big photographic plate, and he sees here, if I can find it, out there, a star, and he realizes it's a Cepheid variable star. Now that object is 1 million times or even 10 million times fainter than the objects like it in the Milky Way. And so he immediately knew that the Andromeda galaxy was a galaxy several hundred times further away than the stars in the Milky Way. So that was the seminal change of view, that technology able to break the deadlock of ideas. And following up on that, in 1929, using that same telescope, he went through and he couldn't see Cepheids. They weren't bright enough in the more distant galaxies that Slipher had looked at, but he could look at the rest of their stars. He assumed that the brightest stars in a galaxy were the same brightness, a very rough proxy, but one that served him well. And what he found out was that the faster the galaxy was moving away, the fainter its stars were. And that allowed him, with this data, and this is the power of data, here's Hubble's 1929 paper, brighter stars to measure distance, fainter stars to measure higher distance, Slipher's measurement of the Doppler shift, or redshift as we call it now, and you see a very rough linear trend. But that linear trend changed our view of the universe because it allowed us to claim that the universe is expanding. Why would you say the universe is expanding? Well, imagine I take a universe, and thanks to my computer, I expand it, and I overlay before and after. What do I see? Relative to my vantage point, I look out and I see nearby objects. As I've expanded the universe, I've moved a little bit. Nearby objects have a low velocity. Distant objects, they've moved a lot. They'd have a higher velocity. Indeed, you can calculate that in an expanding universe, the further away you are, the faster you move. But of course, it was exactly what Einstein's equations of general relativity predicted for the universe back in 1917. They just hadn't thought of the context of what that meant. So sometimes you can have an idea, and although we talk about the expanding universe now, it's not an idea that had occurred to people, even what it meant. They saw the math, they didn't know what it meant. And it turns out it doesn't matter where you are, all people in an expanding universe see the same thing. But we should think now, a little side, that science is messy. I told you how Einstein's theory was vindicated in 1919 when Eddington went out and did these measurements of the two eclipses. Now, I want you to look. This is the real data. This was the data taken by Cromwell, who was by Eddington himself, Principia, and it's cloudy. You can't see any stars. This was taken by the Astronomer Royal, and you'll see all the stars are donuts, and that's because the Astronomer Royal, the professional, didn't manage to get his telescope in focus. It is from this data and those stars that Eddington made the measurements that showed that space was curved as per Einstein's theory. Eddington was an incredible proponent of Einstein's. He was a theorist, and people who work on data never let theorists near data. This data has been since reanalyzed long after Eddington departed, and it's realized that there was no possible way the data were good enough to make the claims that Eddington did. That is what you call confirmation bias. Eddington didn't cook the books. He worked on it, but he wanted the answer to be something. And when you want the answer to be something, you will often get the answer you want, whether or not you realize you're doing mistakes or not. The real work that showed this to be true happened in 1922 in Australia by a group of Canadian, American, Australian, and French researchers. And there they had proper equipment, proper measurements, and this is their measurements from that eclipse in 1922. But you've never heard of them. They get none of the credit. That's where science is messy. You do get credit for getting the right answer ahead of your time for the wrong reasons, I'm afraid. Another case in point, Georges Lemaitre. Here Georges is with Einstein, and if Georges is looking a little uncomfortable, let me explain why. 1923, he was ordained as a priest. He's Belgian. He came to the United States, enrolled for a PhD at MIT, but returned to Brussels to do most of the work. In 1927, he published his PhD thesis, A Homogeneous Universe of Constant Mass and Growing Radius Counting for the Radial Velocity of Extragalactic Nebulae, e.g., the universe is expanding, and I've derived the equations of Einstein's theory to show it. And I've showed that using this data that this guy named Edwin Hubble has out on the web, or whatever it was at the time, I can see that it's actually happening in nature. Lemaitre made the mistake at the Solvay conference in 1927 of showing it to Einstein, who said of his work, your calculations are correct, but another guy by the name of Alexander Friedman already did it 4 years earlier. but your grasp of physics is abominable. Einstein was unwilling or unable to understand the expanding universe. So Lemaitre, who in 1931 also discussed the idea of the primeval atom, which everything grew out of, the Big Bang, has been largely lost from history. Salesmanship is important. Hubble went to the New York Times. Lemaitre didn't. Edwin Hubble is famous. Lemaitre is not. Probably both of them were equally happy. Do not think that fame in your science is going to make you happy. Getting the right answer and doing well is ultimately what will drive you. So I don't actually feel as bad for Lemaitre as you might think. I think it's a miscarriage that he didn't get credit for what he did. That's why I'm telling you today. But in the end, I think Lemaitre was a happier man than Hubble was as he grew older. All right. By 1936, cosmology's foundations were set as we know it today. The universe was assumed, this was their axiom, that to be homogeneous and isotropic. That means it has the same properties everywhere, the same average density, it's not rotating, it has no preferred direction, and that allowed you to then take the equations of general relativity and solve them. I told you how hard they are to solve. This allowed them to be solved. That was a very important bit. It turns out that those statements right now are still true today. This is how we understand the universe. Those ideas are really all in place from 1936. There is a subtlety, though. It's just that when you look at something like the expanding universe, our idea under general relativity is that it is space expanding, and that the spectral shift is not a Doppler shift. It's actually the expansion of space itself, a subtle difference. Now you could imagine if the universe is expanding, we can run it in reverse. What happens? Things get closer and closer and closer, and that naturally brings you to the idea of a Big Bang. Like Lemaitre realized in 1931, like Gamow realized in 1948, but turned out to be a big surprise in 1964 when Penzias and Wilson, using a radio telescope, went out and saw that there was a hissing at 3 degrees, as it was known at the time, a 3-degree black body hissing in all directions in space. This is what our best measurements of it look like now. Their measurement would have been that thing just being a nice white picture, everything looking more or less the same. That idea, that what we're seeing there, that is the remnant of the Big Bang, known as the cosmic microwave background. So as the universe was more and more compact, the photons that are in the universe now were of smaller and smaller wavelength, and eventually they had a temperature that instead of being 3 degrees like it's seen now, was more like 3,000 degrees. And 3,000 degrees is the temperature where hydrogen goes from being ionized to neutral. And so what we're seeing here is the universe doing that change 380,000 years after the Big Bang. And when the universe is neutral, it's transparent because electrons are what light like to scatter off of. And when it's ionized, the universe is opaque. So you're looking back through a transparent universe to 13.8 billion years ago, and bam, you suddenly hit a wall of electrons. And that wall of electrons are what you see there. So we can go through and we can run the universe in reverse. If the universe is expanding now, it's expanding at some rate, which means if I have two galaxies separated in time, I just take the expansion rate of the universe back, and I naturally can figure out how old the universe is, the time of the Big Bang from that expansion. Now, I thought that was an interesting thing to do because it had been such a controversial topic. Here is the value of the Hubble constant over time. Now, I've used astronomers' units here, but just to give you, this is about a 2 billion-year-old universe. This is about a 20 billion-year-old universe. So when Hubble made his first measurement of the expansion rate of the universe, it said that the universe should only be 2 billion years old. So you run it into reverse. We already knew the universe was older than that because the Earth was about 4.5 billion years old. So you can see that the initial measurements have been very bad, but they'd sort of settled down from the 1980s into a sort of a band. If we go in and we zoom into that band, this is what it looked like during my lifetime. We sort of had a band of a universe that's roughly 8 billion years old and one that's 20 billion years old. And to make things worse, there were two groups. There were the low group and the high group, and only a few people in between. So when I started my PhD, this seemed like a big question. I always tell people, answer the biggest questions that you can, that you think you can answer. No sense going after a big question if you have no chance of answering it, but something you're really interested in. And so I embarked on my PhD with Bob Kirshner at Harvard, starting in 1989. And 3 years, 11 months, and 4 days, but I wasn't counting. Here I am showing my answer to my PhD supervisor. And the answer I got, well, that is the accepted value now. That little band and my band was right there in the middle. A universe about 13.5 to 14 billion years old. Now, I was not the person who discovered the age of the universe, but I was part of the conversation that allowed us to converge down to the accepted value that we have now. And being part of that conversation is what any good thesis is about. You can't expect to be the person to change the universe or our view of the universe, but you can hope to be part of the conversation, and that's all should ever hope to be, because you never know what you might discover when you're in that conversation. So the Hubble constant tells us the age of the universe, and as I said, that value was about 14 billion years old, is what we think how old we think the universe is. Life's a little more complicated. I'm going to just briefly flash to you how general relativity works in one slide. You don't have to worry about this. But if you take those equations and you assume the universe is homogeneous, you can take those 16 equations that are linked together and you can break it down to 2 equations, which are known as the Friedmann equation. This is the Friedmann equation for the universe. It's a nice ordinary differential equation. Still means it's hard to solve because differential equations are always a pain. But just to show you how simple it is, you got the speed of light, you've got big G, the gravitational constant, you've got the density of stuff in the universe. Turns out, as I'll show you, you have the curvature of the universe that you need to worry about. And then you have this one thing, the scale factor as a function of time. The scale factor tells you how big a piece of the universe is of time. That's the differential equation you have to solve. That's the thing that's been in place since 1936. And so if you solve that equation, you get different answers. If you have a universe, for example, that has nothing in it, you get the straight dotted line, yellow, over time. Universe just keeps getting bigger and bigger and bigger over time. Doesn't slow down, doesn't speed up. On the other hand, if you have more and more stuff in the universe slows down faster and faster. Such that, although all these universes start with a Big Bang, and you can see how old the universe is actually depends what's in the universe, only one of these universes, that's a very heavy universe, ends with a Gnab-Gib. That's the Big Bang backwards. So if you go through and see what the universe is doing back in time, you can also figure out what it's doing in the future by solving that equation. So that mathematical framework allows us to test the framework of what's going on in the universe. So slowing down of the universe affects how old we think the universe is going to be. It tells us the ultimate fate of the universe. And it turns out it also tells us the shape or weight of the universe. So a heavy universe is finite. Space bends onto itself with time in a 4th dimension. It's a universe that has a finite volume. So universe, if I head out that direction, I eventually come back to where I start. Hard to visualize? Yes. Mathematically, easy to write down the equations. A light universe bends away from itself in the shape of a saddle with hyperbolic geometry. And the just right universe, which has just the perfect amount of matter in it, is balanced, such that space neither bends away from itself or onto itself. The 3 dimensions go out to infinity in all directions. Now, it turns out that the more stuff you have, and it doesn't matter what's in the universe, photons, atoms, cosmological constant, they all contribute to the stuff of the universe that make its shape. So if you could measure the shape of the universe, you would know how much stuff was in it. So I moved to Australia in 1994, and that presented an opportunity to measure the universe's past. Imagine you could measure how fast the universe is expanding now and compare to what the universe was doing, let's say, 6 billion years ago. How would I do that? I would look at objects far enough away that their light would take 6 billion years to reach us. I can look back in time in our universe. I can't look forward, can only look back. Imagine if I do that experiment that Hubble did or I did for my thesis, and I saw what the universe was doing now compared to 6 billion years ago. I could see if the universe was slowing down over time at a rate such that gravity would win and the universe would eventually end, or gravity would lose and the universe would go on forever as an infinite universe. That seemed to me to be a question I could explain to my grandmother. Another one of my suggestions is always make sure you can explain what you're doing to your grandmother. If you can't, figure out how to. Stop your research immediately, figure out how to explain it to your grandmother, and then proceed. This I could explain to my grandmother. Of course, she asked me, why are you doing this? They pay you to do this? But don't worry about that. And so the reason I was able to do this is because there was an opportunity. The opportunity was I was moving to a new country. I could reset and start doing everything from afresh. New pair of eyes. No one to slow me down. I was in charge of my own destiny. And so there were changing times in my own life. There was changing technology, which I'm going to tell you in terms of new telescopes and detectors. And there was also changing knowledge. The same ingredients that go through every other time I've talked about, be it Copernicus and the Renaissance period, Galileo with telescopes, Newton with mathematics. So the knowledge was caused by a group I had worked with my PhD thesis, a group in Chile who had been working on supernovae. Type 1a supernovae were what they were working on. What's a type 1a supernova? Well, to understand a type 1a supernova, let's just have a quick review of our sun. Our sun in 6 billion years is going to puff up, become what we call a red giant, destroy the Earth, and then collapse down to a tiny little star called a white dwarf. We call that an electron degenerate star for those who know quantum mechanics. And binary stars, well, you get a similar but different process where, hopefully, if you look at a binary star, you get a very complex interaction that occurs as the first star puffs up to become a red giant. It eventually will shrink down and become a white dwarf, just like the sun. And then you have a white dwarf orbiting another star that's had a bunch of stuff added to it. That star will eventually go through its own evolution, become a big red giant, and will eventually be able to dump material back on to the first star, to that white dwarf. And so when that happens, the white dwarf from the first star will slowly grow in mass. And Chandrasekhar, one of the main reasons he won a Nobel Prize is he showed that if you have a degenerate ball of electrons and you take it to 1.38 times the mass of the sun, it goes boom, as a giant thermonuclear bomb, not the size of this desk, but the size of the sun. So these things are very bright. They produce all the iron, or 2/3 of the iron in the universe. And it turns out that they're about 5 billion times brighter than our sun, take 20 days to reach a maximum brightness and fade away. They are intensely bright. We can see them with modern equipment on the other side of the universe, 6, 8, or even 11 billion years into the past. These guys realized in Chile that there was a way of calibrating how many watts these light bulbs put out, and that was something that they used to measure the expansion rate of the universe very accurately, and it provided that idea of how we could go through and trace back the universe back in time. We had something that was accurate and very bright. The other piece of equipment were new telescopes, the 10-meter Keck telescopes that came online also in 1994. They were the first telescopes big enough to take spectra of distant objects. But you also need to find those objects. They're very rare, and for that we needed digital detectors in the form of large format CCDs. We all know large format CCDs or CMOS devices because we all have them in our phones. But we got our first 4-megapixel detectors in 1994. Seems small now, but it was huge back in 1994. You guys didn't even know what a digital detector was back then. Probably a lot of you weren't even born then, but anyway. So that was a huge advance in technology. Now, we weren't the only team that had this idea. There was actually 2 teams that realized that this program could be done then, and so it started a giant race to measure the expansion rate of the universe. Now, the challenge was going through about 50 gigabytes of data, this being like 1/1000th of a night of data. It's a couple thousand galaxies there, and you got to find the exploding star. They're very rare. They only happen in a galaxy like the Milky Way every 300 years or so. And so I'll help you in this case. Exploding star is this one. So what you have to do is go through, process that data. We take 2 images, and you look for things that have changed, and part of my job as a young postdoc was to write the software that would go through and match these images up automatically and find the things that had changed. That is a supernova from 5 billion years ago. That supernova exploded before the Earth was formed. Shows the power of what you can do in astronomy. So I'm going to take you to a trip to Chile, because this, of course, is a team effort. And while my software was useful, it needed a lot of help along the way. There's Greg Aldering from the other team, because they needed the same equipment we did. It was only one place in the world, and we all share. And so they needed the same equipment with these big digital cameras. Here at the Cerro 4-meter, as the star goes by, we get 6 nights a year. We have the largest program on the facility, 6 nights a year. So the time is very precious. As the data comes down, my software is there finding things. It finds asteroids, it finds glitches, and it finds supernovae. And we literally have a sweatshop of people in Chile all poring over the data, trying to figure out what are the little explosions and what are not. Time is of the essence because 12 hours or 36 hours later, depending on the day, we go and we have to send our finding charts of these objects to the Keck telescopes in Hawaii, where we have, again, a few nights a year to get the spectra of the objects that we think are these exploding stars. And who's there with us? None other than Saul Perlmutter from the other team, because again, that's the only telescope in the world that can do that side of the equation as well. So although it was very competitive, we also did get to see each other all the time. So in 1998, this is what our data looked like. Each supernova is got an error bar here, 1 sigma, 68% confidence level, and you can see the nearby objects and the distant objects, and you can look and realize immediately that these objects do not lie in the bottom part of the diagram. It was obvious immediately that the universe was not finite and was not going to end. But when you did a statistical analysis, you realized that the chances that this group lie in the yellow part of the diagram was only about 1 in 1,000. It was about 99.9% confidence against. Now, the particle physicist in the room will say, well, that's not very good. The biologist would say, why did you wait so long to publish? In astronomy, we're sort of in between. So 99.9, if everything was perfect, you'd say fine. But there's always little errors. There's the unknown unknowns you have to worry about. So we presented a paper. We started writing a paper called Evidence. We did not describe it as a discovery. And people asked, well, did you have a eureka moment? And the answer was no. We just thought we were wrong initially, and we had to spend a lot of time reproducing the results until we said, God, we're going to have to publish this. As we did this, the other team, of course, was working on their data, and unbeknownst to us was getting the same answer. And so we ended up in 1998 with two publications. But to give you a sense of how science works, I'm going to give you a few quotes from our team during this time. Alex Filipenko, who Adam was working with at Berkeley at the time. Adam showed me fantastic plots before we left for his wedding. He was just getting married at this time. Our data imply a non-zero cosmological constant. Who knows? This might be the right answer. Bruno Leibengut, who's in Swiss, quite conservative, good friend of mine as well. Concerning a cosmological constant, I'd like to ask Adam or anyone else in the group, they feel prepared enough to defend the answer. There's no point in writing an article if we're not very sure we're getting the right answer. Bob Kirshner, who is both Adam's and my PhD supervisor. I am worried. In your heart, you know the cosmological constant is wrong, though your head tells you that you don't care and you're just reporting the observations. It would be silly to say we must have a non-zero cosmological constant only to retract it next year. Mark Phillips in Chile, one of the people who developed the technique. As serious and responsible scientists, we all know that it is far too early to be reaching firm conclusions about the value of the cosmological constant. John Tonry in Hawaii, who remembers the detection of the magnetic monopole or other gas? On the other hand, we should not be shy about getting our results out. Alex Filipenko, who is just down the road from Saul Perlmutter, if we're wrong in the end, then so be it. At least we ran in the race. Alex was very worried about getting scooped. Alejandro Clocchiati from Chile, he's an Argentinian, has the best quote, "If Einstein made a mistake with the cosmological constant, why couldn't we?" And Nick Sunsef, who helped form the team with me back in 1994, I really encourage you to work your butt off on this. We need to be careful. If you are really sure that the cosmological constant is not zero, my God, get it out. I mean this seriously. You will probably never have a scientific result that is more exciting come your way in your lifetime. So sometimes you get lucky, which is exactly what happened. We went out to do a perfectly sensible measurement and got a perfectly nonsensical answer. And that's how science sometimes moves forward. So there were two papers because the other team was getting the same answer as us at the same time, and it is for that that our teams, respective teams, won the Nobel Prize. Here is our team together for the first and only time at once. We have worked by the internet, and shows what you can do with people on 5 continents here, and the other team, of course, was there as well. So what is pushing on the universe? Well, Einstein's idea of the cosmological constant seems to work. We're not sure that it's right, so we give it the euphemism dark energy. If you go through and do a detailed analysis of our results, we needed the universe to be a mix of 30% normal stuff and 70% stuff that pushes. You can imagine that there was some questions about this result when we did it. So one of the first results was going out and making a map of galaxies. It turns out the foam structure of these galaxies allows you to weigh the universe. Essentially, that foam structure tells you how much gravity there is. And the team that did this in Australia and another one in the United States both concluded that the amount of gravity pulling on the universe gets you about 30% of the way to make the universe just right. So this tells you how much normal matter there is in the universe. But that is, of course, 5 times more gravity than there are atoms. And that brings us to a topic I'm not going to talk about. Dark matter is that the stuff we see in the universe is dominated by stuff we don't see, even when it comes to normal gravity. So dark matter, we don't know what it is. Others will talk a bit about it. It might be some undiscovered particle that, like a neutrino, weakly interacts and, for example, travel right through the Earth. It would have gravity just like atoms, but is essentially invisible because it is only through interactions that we see things. And the good news is we can't see it, it can't see us either. The other experiment that came along was this measurement of the cosmic microwave background, because these are sound waves splashing around the universe. And the size of those sound waves is modulated by the fact that the sound waves have been traveling for about 380,000 years, and because of the speed of sound and the fact that they get dragged along with the expanding universe, the largest sound waves should be about 450,000 light years long, and that's a number we know very well. The physics here is very well understood. So you can look at how big those bumps are and use it to compare to how big those lumps really should be, and that, it turns out, allows you to measure the curvature of the universe, because the curvature of the universe distorts the images. And just like a mirror will distort things to make it look smaller or larger depending on the shape of the mirror, the shape of the universe distorts the universe. So the experiment such is that if the universe has hyperbolic shape, the bumps are small. If it's finite and curved onto itself, the bumps are large. And if it's just right, they're in the middle. And it turns out the measurements we have made of this indicate that the universe is within 0.3% of being just right. But remember, this doesn't care about stuff that only makes gravity pull. It also is okay for stuff that makes gravity push, or photons, or anything you can think of in the universe. So that allows us to do some subtraction. All matter adds up to 100%. The gravitationally attractive matter is 30%, leaving us with 70% mystery matter, the same stuff that we need the universe to be pushing the universe apart. So you put it all together, what do we have? Well, we have a bit of a mess. We have a universe which is only 5% of the atoms that we know, love, and study here on planet Earth. 25% of the universe is dark matter, stuff that has normal gravity, but seemingly is invisible. 70% is dark energy, stuff that's part of space itself and pushing the universe apart. So you might well ask, if I need to make up 95% of the universe to understand it, doesn't that mean we just don't understand anything? And that would be a reasonable assertion. But the reality is that this crazy model predicts everything that we yet have observed. Here is the actual acoustic measurement in terms of a power spectrum, but think of taking an oscilloscope of the early universe. And the data, which show this very complicated accordion sonic signal, this acoustic signature, that was predicted back in 1998 from our data and matches exactly with what now has been measured in advance. That's like saying, I have a theory of Beethoven's mind, and I predict the first 4 notes of his 5th symphony, and you do it, and you get dun 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 dun, and you get it right. If you can do that from first principles, you probably do understand Beethoven's mind. This theory is crazy, but it works incredibly well. So what does it predict about the future of the universe? Well, the universe is in a battle between dark matter, which doesn't expand with the universe, and dark energy, which is created as the universe expands. And so, for example, as you look back in time, the universe will be more dense with things like atoms and dark matter. Because as space, each cubic meter of space is smaller, there's more and more stuff in it. It gets crammed into a smaller volume. Dark energy density stays the same, and so there's a balance of what runs the universe over time. In the past, the stuff which makes gravity pull was stronger because it was more dense. Dark energy probably hasn't changed at all. So you really get a battle of domination of the universe of dark energy versus dark matter. And it turns out 6 billion years ago, dark energy took over domination of the universe and has been pushing the universe apart ever since. So the future of the universe seems to be dark energy. The more space expands, the more dark energy is created, the more dark energy is able to overwhelm everything else in the universe, the more dark energy can push on itself and speed the expansion rate of the universe up. Eventually, the creation of space will happen even faster than light can travel between objects we see today. So galaxies we see today, their light will travel through space, but will never reach us because space is getting created so quickly that the photons literally get stranded on their way to us. The most distant galaxies we see today, their light will never reach us. That's emitted today. Now, does that mean we're going to be ripped to pieces? No. That is the density of dark energy. There's not a lot of it out there. That is the density of Earth. We're a special place in the universe. The gravity of attraction here is much, much stronger than dark energy. And remember, the density of dark energy is not changing over time. So the Earth is safe, except for the sun, which will destroy us in good time anyway. But in our part of the universe, there is a sphere where the amount of stuff, of gravity, attractive gravity, exceeds the density of dark energy. And our part, our little sphere, which includes us and a couple galaxies, is secure in the future. Eventually, within that sphere, the galaxies will merge, and for example, the Andromeda spiral and us will merge together to form a supergalaxy. But we will look out into a universe where there's nothing else 100 billion years from now. All the other galaxies that we see will be so far away that their light will effectively not be able to reach us. We will look out onto an island universe like Shapley conceived of back in 1920. So that tells you an interesting fact. We live at a special time of the universe. All times in the universe are not created equal. You are losing information out of this universe very quickly. In 100 billion years, we will not be able to know what we know about it right now. But the reality is, until we understand what's accelerating the cosmos, anything is possible. Dark energy can change, doesn't have to be what Einstein said it is, and could make the universe speed up, slow down, or do whatever a theorist with a pen might decide. Predicting the future requires infinite knowledge. And that is a quandary we have within my field. Nothing in the future is for certain. So that leads us to where I want to finish, which is the impossible questions of cosmology. And I put a question after it because I don't know these are impossible. I suspect they might be. Is the universe infinite or finite? We know it's within 0.3% of being at the razor's edge between finite and infinite. How do we measure something that's on the knife edge? You can't. So the universe is much, much bigger than the universe we see, but we cannot know, it would seem, if it's infinite or finite. We cannot measure that if it's close enough to that razor's edge. And it seems to be very close. People always ask, what came before the Big Bang? Or what is the Big Bang? I don't know what the Big Bang was. I only know that it occurred. I can talk about things that happened after the Big Bang, but not the Big Bang itself. Perhaps there's some higher level of physics that will illuminate this, but it may be that there isn't. It may be that that is a piece of information that's effectively impossible to sort out from what we know here in our own universe. And that leads to the question, are we part of a multiverse? What's a multiverse? Well, it has two flavors. One, we have our universe created 13.8 billion years ago, and there are disconnected universes separated by these extra dimensions popping up as well. Well, they may be or they may not be, but if I can't test they're there, that is an idea that's untestable. The other idea is that maybe our universe is infinite or quasi-infinite, and it slowly changes and morphs into a completely different set of rules if you get far enough away. Again, very hard to test, although you might see the rules of our own universe drifting ever so imperceptibly across our own universe, and that might be a way to test it. So I don't know what the future of the universe is, but I do know that unless dark energy suddenly disappears for reasons I can't possibly guess, and I think are unlikely, the universe will at an ever-increasing rate expand, fade away, and leave me and my fellow cosmologists without a job. Thank you.
Thank you very much, Professor SCHMIDT, for very interesting lecture. Now the session is open to questions and comments, but we don't have much time, about 5 minutes or so, but please feel free to raise your hand.
For the result, yeah, for the result of two competing group proving the accelerating expanding of the universe, you mentioned that the two groups share the same equipment. So what's the difference of methodology between the two groups?
So you are correct that the methodology between the two groups were similar. I mean, there were independent codes. We both used exploding stars. We used different ways of analyzing the exploding stars, different tools to go through, and once you have the distances out of those exploding stars, to analyze them within the context of the model. But the two methods were quite similar. It would be analogous to CERN using two teams doing the same chains to see, to determine the Higgs. So there was overlap, and that is why people didn't immediately in 1998 and say, wow, this is right. They said, wow, this is interesting and surprising. We need to check it, which is the only sensible thing for them to do. But the methodology between the two teams was independent but quite similar.
Thank you for the very informative lecture. So up to date, whatever we know that the velocity of light is maximum in the universe. But we came to know that the universe is expanding faster way than the velocity of light.
Right.
Which one is actually?
So light has a finite value of speed of 300,000 kilometers per second. But the expansion of the universe can happen faster, because what is that space? Space is space. It's not the motion of things. So the fact that the universe is expanding faster than the speed of light does not violate the idea of information or anything traveling faster than the speed of light. So light continues to travel 300,000 kilometers per second, but it's the actual medium that it's traveling in that is expanding. And so I like to think of it as sort of the rubber band, and imagine if I take a rubber band and I expand every centimeter of the rubber band by 1 centimeter per second. Seems reasonable. I can do that right here. But imagine that rubber band is longer and longer and longer. Then eventually the ends of the rubber bands, if I do that, are traveling faster than the speed of light. Now that will break the rubber band. It will not work because that's actually a physical entity. But if you think of space, which really isn't a physical entity, it is okay and it's allowed. One more?
Thank you. Wonderful lecture. In terms of these theories about what came essentially before things now, the origin of the Big Bang, what came before it, and the nature of that very first moment of the universe, I mean, of course, there are all kinds of theories about how the universe started as like a four-dimensional black hole or something, then collapsed into something, then exploded in the Big Bang.
Yep.
Do you think that such kind of conjecture is fruitless at the moment, given that we don't really have the means to look beyond that?
So I wouldn't say it's fruitless, because the only way we'll ever be able to test it is if someone comes up with an idea where you say, well, if this is true, it will actually have manifestations in our own universe that will allow us to test the idea. Now, it may well be that there is no information leaks into the universe from before the Big Bang, or maybe there is information that leaks in. You will only know that there is if you have people thinking about it. On the other hand, until we start sorting that out, I mean, all bets are off of which idea is right. And so I do go to conferences sometimes where people become very heated in their belief of which idea is right. But since there is no evidence to support any of it, I am what they call an agnostic on those ideas.
Thank you.
With the structure of galaxy, would there be points where
gravity would be overpowered by the expansion and here the galaxy to shrink, so to speak?
So it turns out that you saw the density of the dark energy is very, very low. And so if you look at our galaxy, the density, even on the outer reaches of the galaxy, is several orders of magnitude more dense than the dark energy. That being said, what will happen in the very distant universe is these galaxies will merge together, and then you'll get a process of evaporation. Stars, you can just think of as just being like a little molecule inside of a glass, and some of them in the interactions with each other get some extra velocity, they evaporate. They'll go flying off with escape velocity from the system and be lost to the expansion of the universe. Eventually, stars themselves are made up of protons and neutrons, and there are thoughts that even those might be unstable on very long time frames. So it might be that eventually even the stars will evaporate, and eventually we'll end up with a universe that literally has nothing in it. But that's very speculative. That's trillions upon trillions upon trillions of years into the future.
Really a wonderful talk. I've never really studied physics, so I may be asking a very silly question.
That's all right. We like silly questions.
Okay. Well, it seems like a lot of the sort of estimations and predictions have relied on this idea of future and past, and essentially just kind of using time as a ways to predict things. So I guess my question is time a constant thing? So is the time that we experience now, does time function the same when you go billions of years in the past and billions of years in the forward? And would that change everything that you've kind of told us about?
Yes, so time is a very funny thing within physics. Time is treated as the metronome of which things happen. So imagine that I managed to speed up time. That would mean all the physical constants of nature would change as well, because they're all measured in things related to time. So time is the thing that we keep constant within our physics equations typically. And although you can, as an individual, move forward in time, there's no evidence that you can move back in time and probably would cause bad things to happen in the universe. From a physics point of view, we keep it typically as the constant thing between everyone. And then we can test for consistency and say, are things like the constants of nature the same when we look back 8 billion years ago? Did the nuclear reactors in Africa that are naturally occurring behave with the same laws of nature as today? And the answer is, as near as we can tell, yes. The laws of nature are constant, but they really do hold together by this single thing, time. And I once had a kid say, well, define what time is. And I can't define what time is. Time is defined in terms of everything else. It's a big circular, self-consistent reference within physics. It doesn't really have its own definition. So I realize it's probably not a completely satisfying answer, but it's the circular nature of how we treat time in physics. Maybe Mr. Kobayashi would, or our particle physics theorist, yes. Okay. All right?
Probably you have many more questions, but we are really running out of time. Professor Brian Schmidt will have 4 discussion sessions today and tomorrow, and you can ask questions there or during breaks. So let's thank Professor Schmidt again.
Thank you.
Thank you very much, Professor Schmidt and Professor Natsume. Now we would like to take a short break. Please come back to this room soon. We will start next session from 11 o'clock. Thank you.